Okay, so we've just covered the idea of field strength. We're now going to move on to the concept of potential and the potential at different points in a field. So here's a working definition of potential that we're going to go with for the moment. We're going to adapt this later, but hopefully this will make sense for the time being. That potential is the potential energy per unit something at a point in the field. What on earth does that mean? Well, again, the something is the thing that interacts with the field. So the gravitational potential at a point in a gravitational field, we're going to define as the potential energy, the gravitational potential energy per unit mass at that point. And if it's energy per unit mass, then the unit is in joules per kilogram. The electric potential is going to be the energy per unit charge at that point in an electric field, and the unit is going to be in joules per coulomb. And conveniently, both of these have the same symbol V for potential. So potential is the energy per unit mass, or the energy per unit charge at a point in a field. Now, what on earth does that mean? How can we calculate it? Well, let's do an example, and hopefully it will start to make some sense. So we'll take a uniform gravitational field, like the field in this classroom can be approximated to. We'll assume that G is 10. The gravitational field strength is 10 newtons per kilogram. And in this example, we can say that the gravitational potential energy is just going to be mgh, mass times gravitational field strength times height. Now this is only true in a uniform field, okay, because G is constant. In general, this is not the case, okay, but we can use this because we're in a uniform field. Now, the other relation we need is that potential is gravitational potential energy per unit mass. So the potential at a point is the gravitational potential energy divided by the mass. Right, well, let's get cracking and see if we can work this out for our test mass, which is over here. It's a 5 kilo test mass, which is very small when compared with the mass of the Earth. So what we want to do is work out the potential at different heights. So we'll start with the potential down here, which is going to be the gravitational potential energy divided by the mass. And the gravitational potential energy is going to be mass, 5 kilograms, times G, 10 newtons per kilogram, times height, 0, divided by the mass of the object, 5, which is happily going to give us a potential of 0 joules per kilogram. So the potential down here is 0. Simples. Alright, I've now lifted it up a metre. What's the potential in this field at this point here? Well, the potential is the gravitational potential energy per unit mass. So now V is going to be mass 5 times G 10 times H 1, all divided by mass 5, which gives us 10, so it's going to be 50 divided by 5, 10 joules per kilogram. So the potential at this point in the field here is 10 joules per kilogram. Now if you keep moving this up, I'm sure you can imagine what's going to happen. The potential is going to keep going up by 10. Let me just move all this working out of the way so it doesn't confuse matters. So what the potential is telling you is how much potential energy a unit mass at that point would have. Okay, so here at this point, at 1 metre in height, each kilogram has 10 joules of gravitational potential energy. So if I've got 5 kilograms, it's going to have 5 times 10, 50 joules of gravitational potential energy. Here, each kilogram has 20 joules of potential energy, so now my mass is going to have 100 joules of gravitational potential energy. Up here, it's going to have 150 joules of gravitational potential energy. So basically, potential is just like gravitational potential energy, but taking into account the mass of the object, so it's the gravitational potential energy per kilogram of the object. Now, I'm sure you can imagine that if I took a few paces to the right, and did this whole thing again in the classroom with this uniform field, I would get exactly the same set of potentials going up in height. So we'd have 0, 10, 20, 30 joules per kilogram. Now what we can do with all this, let me just remove all this working. What we can do with these is join them up. So if I join up all the places with a potential of 10, I get that line. If I join up everywhere that has a potential of 20, I get this line. If I join up everything that has a potential of 30, I get this line. If I join up everything with a potential of 0, there we go, I get this line here. And these lines of equal potential are called equipotentials. So, equipotentials link points of equal potential. They're a bit like contours on a map. So on a map, contours link points of equal height. So the 200 metre contour links up all the different points that are 200 metres high. So equipotentials are similar. They link points of equal potential. Now, in a uniform field, the equipotentials are equally spaced lines, or actually, technically, they're equally spaced planes. So if we have a quick look back at this, our equipotentials look like lines, but actually, if we then were in the classroom and we took 2 paces backwards, we would get exactly the same potential, and 2 paces backwards again exactly the same potential. So these equipotential lines are actually planes, they're actually surfaces. So the 30 joules per kilogram equipotential in the classroom is everywhere that is 3 metres above the floor. That is an entire plane of equipotential. The 0 equipotential is the entire floor of the classroom. So in a uniform field, these are equally spaced planes, the equipotentials. In a radial field, just out of interest, what would the equipotential surfaces, the equipotentials, be? Well, if we nip back to our radial field that we had somewhere, we'll use this one, why not? Okay, for the Earth. Where has the same potential? Well, ground level, a bit like the floor of the classroom, we could say that that is an equipotential. It has the same potential energy. If you took an object around the surface of the Earth without lifting it higher or lower, then it would have the same potential energy everywhere. Likewise, if I lifted an object 100 metres up, it would have this potential. If I took that anywhere on Earth and it was still 100 metres up, it would still have the same potential. So, for a radial field, the equipotentials are spheres. So you've got to imagine that these circles are actually spheres. This one a sphere that covers the Earth, the surface of the Earth. This one a sphere that is always 100 metres above the surface of the Earth. So equipotentials join points of equal potential. Right, so we've got quite a long way. We've mapped fields, we've looked at different shapes of fields, we've introduced the idea of field strength, and now we've briefly covered potential. So we've pretty much done these things on the list, but what we're going to do next is just quickly look at the relationship between the field strength and the potential. So that's what the next video will be about.